Okay. Okay. Hi, everyone. My name is Yulia. I work for Anoma, and I'm going to present you Taiga. So, thank you. So, here's the Taiga team. Alberto, Joe, Shuyang, me, Vasil, and Simon working on bringing Taiga to the world. Yeah, everyone will appreciate that. So, back to Taiga. What problems Taiga solves? So there are projects that provide counterparty discovery and atomic matches, like OpenSea, for example. There are projects that provide shielded state transitions, like Zexi. And maybe there are not projects that provide private account abstraction. I'm not aware of that, about their existence. But Taiga aims to provide all of these features in single product. So that's what we're gonna talk about. If you're confused about the relationship between Taiga and Anoma, Taiga is a part of Anoma protocol, and it takes care of shielded state transitions. But it can also be used as a standalone component, provided a data storage. Here's Taiga overview in one slide. It looks a little bit too much, but we're gonna look through it one by one. So Taiga is an operating system for distributed applications. It means that you build applications on top of Taiga, and Taiga takes care of running them, right? Taiga is UTXO-based, so each transaction is a list of input and output nodes. I'm going to talk about nodes a lot, maybe, here. So forgive me. So applications built on Taiga have states, and the state consists of nodes. And every node belongs to some application and is a part of the application state. Taiga provides full programmability. We use validator predicates, which are declarative smart contracts, and they're also used to define authorization logic, which is account abstraction, right? Taiga is shielded. It provides data and function privacy. I'm going to talk about that a bit later, and everything else, to be honest. It provides atomic state transitions of arbitrary complexity, also later. It's intent-centric. It's built around intents, which are just user preferences. And counterparty discovery is also taken care of. So if you want to perform some action, you don't need to look for the parties yourself. So now let's dive a little bit deeper and talk about atomic state transitions and intents. So what is an atomic state transition? So imagine we have like parties, Yoshi, Bowser, and Mario. They all want something and want something in exchange, but we can see that one of the parties cannot satisfy any of the other. They could satisfy each other in a three-party bartering cycle. But in most of the systems, it's not possible to do it in a single transaction, which is actually not good because Yoshi, when he goes into intermediate state, might end up in this intermediate state, which is not desirable. Yoshi never wanted this mushroom. Yoshi wanted a star, and now he has to deal with the mushroom. So what we want to do is to allow only atomic transactions. So Yoshi either gets what he wanted or stays in the same state. And here is how to achieve this. It's like a short version. So desired state transition is expressed as intent. And solvers are the actors who receive intents and match them together to produce transactions. And I'm going to talk about these details now. Let's start with partial transactions. Partial transactions are building blocks of transactions. But to understand what a partial transaction is, we need to define a valid Taiga transaction. So, as we remember, transaction is input and output nodes. And it has to satisfy two conditions in order to be valid. It has to be approved and balanced. What does it mean to be approved? It means that all applications involved in a Taiga transaction approve the transaction. If a node is a part of the transaction, it means it the application must approve this transaction, right? And balanced means that for each application involved in this transaction, the total value of input nodes equals to the total value of output nodes. So that makes a valid Taiga transaction. It's approved by applications and balanced. And such transaction can be published on the blockchain. So a partial transaction is also input and output nodes, but it's only approved and not balanced. Such transaction cannot be published on the blockchain, but the idea is that we're gonna build transactions from partial transactions. So on this diagram, you can see that there are two partial transactions, and both of them are approved by applications, which are expressed as validity predicate satisfaction, but they're not balanced in the gray application type in the bottom. But if we combine them, they become balanced, and this is a valid transaction. So that's how we're going to build it. But what about intents? How users express their preferences? So as I mentioned, intents are a way to do that. And before intents, users would have to specify how exactly achieve what they want, and it might not always be achievable in a single transaction, but transactions were the only thing we had, right? And now users have intents, they just express what they want, and then they don't have to think about how to achieve that. Solvers do that. So to make sure that intents are satisfied, we have intent application, which is an application on Taiga, one of the examples. So let's talk a little bit about Taiga applications. Taiga applications have a state and logic. State, as I mentioned, is expressed as application nodes, and logic is a validator predicate. So using an application means creating or consuming application nodes by the rules defined in the application logic. So back to the intent application. So intent application nodes are called intent nodes. We call them intent nodes. And here's how you use it. So when you create your intent, you attach it to the intent node and send it to the solvers. And while this intent node exists, the transaction cannot be balanced because there is input node but no output node. And the intent node can only be balanced or can only be consumed when the intent that is attached to it is satisfied, which is ensured by the application logic. So the algorithm for the solver would be to satisfy the intent, consume the intent node, and it makes the transaction balanced in this application type. Then solver have to repeat this for all application types, and transaction can be published on the blockchain because it's balanced in all application types. Yeah. So a little bit about solvers. As I mentioned, solvers are actors who receive user intents and merge them together to produce transactions. So the intent goes to the intent gossip network, and solvers receive it there. So to create atomic transaction of arbitrary complexity, solvers create partial transactions. They share partial transactions with each other, and they add new partial transactions to the received ones until the set is balanced. So to summarize the recipe for atomic state transitions is that intents are used to express desired preferences. Intent application makes sure that intents are satisfied. Partial transactions are used as building blocks of transactions. And solvers update the future transaction with new partial transactions until the intents are satisfied and transaction can be published. And as a result, we get atomic transaction of arbitrary complexity. So just to understand it better, let's apply this to the recipe, to the example from before. So in this case, Yoshi, Bowser, and Mario would create partial transactions containing their intents. In case of Yoshi, for example, it would be a star. They send these partial transactions to the intent gossip network. Solvers receive them. solvers receive them and match the intents. They see that Yoshi has star intent and Bowser has a star, so the star can be sent to Yoshi. Because these are partial transactions, there is no violation of logic. And these 6 partial transactions from the second and the third column are combined into a single transaction that balances. The star goes to Yoshi, the mushroom goes to Bowser, and the egg goes to Mario. And the intent nodes were satisfied and destroyed, and all of this gets published on the blockchain. So now a little bit about privacy. So Taiga provides data and function privacy. But data privacy, I mean privacy of nodes and transaction data like users, amounts, and some other data. We use verifiable encryption for transmitting nodes to the receivers, to the users. Node commitments are used to establish nodes' existence without actually revealing the nodes. And zero-knowledge proofs are used to prove statements about nodes, that they exist, that they are consumed, and other stuff like that. So by function privacy, I mean hiding what application you use, which essentially means hiding validator predicates. And for that, we use Halo 2 recursion. Yeah, we use Halo 2 proven system for basically everything related to ZKP. About the current state of Taiga. Some details remain to be confirmed, but the code and specs are already available at github.com/anoma/taiga. Check it out. And in the future, Taiga will support public, shielded, and private domains, and will be more closely integrated with Ferio, which is threshold decryption, front-running, protection against front-running. So you'll be able to prove correspondence between private state and data encrypted to Ferio using zero-knowledge proofs. Well, that's all I had to tell you. Check out the Taiga repository. Check out the specs. The specs of Anoma also have Taiga section, and you can contact me using this handle on various platforms. And yeah, thanks for coming and listening.
Any questions?
Hi, thank you for the presentation. Maybe this is a silly question, but can you have balanced intents from the get-go? Or do all of the intents need to be matched for a transaction to happen? Can you send like basically a full transaction as a partial transaction?
You don't have to have it as a partial transaction. You can create a full transaction and just publish it. It's not prohibited, yeah.
Thanks for the talk. Is it the case that intents must always be fully revealed to solvers?
That's a good question. They don't have to be fully revealed to solvers. However, you need to reveal a part of it to the solvers currently for solvers to be able to see it. But we're going to work on changing that and having them in a more private state, maybe using MPC.
Yeah, we have one.
Just a quick one. How are solvers incentivized, and how do we know that what they're doing is in the best interest of whoever is submitting the intent?
That's also a good question. I feel like it's better if I answer it after it's like not a quick answer. Yeah.
Okay, maybe yours is quicker. Go ahead.
No, solvers don't know that. They don't have to know that. I mean, if you want to reveal, you can reveal, but by default, they don't know.
Very good. Right, also.
Yeah, it can be anything, but on ANOMA, for example, we use our own consensus protocol called heterogeneous Paxos. I think it's like BFT protocol. Yeah, but basically whatever supports Taiga's features can be used. Yeah.
Can I ask something else? Or
No,
Okay.
we have the next seat. Sorry. You can maybe chat outside of the room. Yeah, thank you. Thank you, Yulia. Thank you.